Hi everybody, welcome back. We're going to talk today about drag forces, lift and drag forces. Now, we've been talking about, for us this is chapter 11, we've been talking about chapter 8. Now, blast from the past here, this is, I think this is the first lecture I did with you guys. I don't know what number that is, but remember, exam 3 material, what we're talking about is viscous flow, not viscositous flow. Let's just redraw this, shall we? We're talking about the effects of viscous flow. That is our goal here. Now, to be able to describe that viscous flow, the energy loss or the pressure loss or whatever the case may be, to describe what's occurring, to model viscous flow, we need to be able to figure out what kind of flow we're dealing with. Now, we said there's two main categories. There's external flow, that is where the fluid is flowing over an object, or an object is moving through a fluid. In both cases, the model is the same. There's really almost no difference whether the fluid is flowing over the object or the object is being moved through the fluid and the fluid flows around the object. In both cases, we'll model it using external flow models. Now, we've been focusing on internal flow. That's where fluid is flowing through a conduit. Right, so that has been our focus up until now. So we've done 2 homework assignments on that. We're working on the second one right now. You guys turned in the first one last week. We're working on the second homework assignment within the area of completely filled conduits. Right, so there's a couple of types of internal flow. Flow where we've got fluid flowing within a conduit. What we've been focusing on is completely filled conduits, and that would be, for us, that was chapter 8. That's in Chengel and Simbala. A little bit later, if we have time, I would like to talk to you guys a little bit about open channel flow. I don't know if we're going to get there. I mean, it's just getting late in the semester, and we lost a week or so because of converting over to online. But in your text, that is chapter 13. Those of you thinking about going into civil engineering, some areas of mechanical engineering sometimes deal with open channel flow. Open channel flow is where the fluid is not completely filling the entire conduit. The entire conduit is not in contact with the fluid. Some of the fluid is exposed to the atmosphere, meaning there's no way to build back pressure. So in completely filled conduits, we can build a back pressure, and we can talk about the pressure loss. In open channel flow, there is no back pressure, so it's a different model, and it's a different way of modeling. That's not, so this, for us, is going to be on exam 3, completely filled conduits. Maybe this shows up on the final, depending on how we get and where we get to. But for us, what we're going to focus on here in chapter 11 in our text, we're going to focus on drag forces. And we're going to focus on drag forces. Now, there's also another component of that. We're going to talk today about lift forces. We're not going to spend a lot of time talking about lift forces. Those of you going into aerospace engineering probably are not taking this class. A lot of aerospace engineering programs around have a different flavor of fluid mechanics, where they don't necessarily, they're not as concerned about completely filled conduits. They're really focusing on external flow, because that makes sense for an aerospace engineer. Anyway, we can expose you to it, but we're really going to focus on the drag forces, and we're going to talk about how they're related just a little bit today. Okay? So that's where we are. We're going to focus on this right here today and see how far we get. Okay, so I've posted lecture 18 notes in Canvas for you. 1 of lecture 18 video lecture, and so you can see here we've got the slides here as usual. Loud pop here. I'm going to make sure my glare is not too bad on that. Okay, doesn't look like the glare's too bad on that. So when fluid flows over an object, right? So let's say I've got an object here and I've got fluid flowing around this object. If this is a solid object, some kind of ball or sphere, fluid's not going to flow through that ball. It's going to flow around that ball. Momentum is changed, right? So let's think about that. We talked about this in chapter 6. We talked about this earlier when we talked about conservation of momentum. We said that as fluid moves, as we change the momentum of fluid, so notice fluid particles are coming in here, they've got one velocity, and then we change the velocity. It's either going to go this way or it's going to go that way. It's got to go around this thing. So you're changing the momentum of that fluid in order for that to happen. Now, what does that mean? How do we change the momentum of a particle? And we talked about this in Physics 1. Think about it in Physics 1. If I've got a particle and I need to change the momentum of that particle, how do I do that? That means if you're not going to change the mass of the particle, you need to change the velocity. How do we change the velocity? We cause an acceleration. How do we cause an acceleration? We apply a force. Right? Change in momentum of those fluid particles requires a force. Newton's third law tells us that as the fluid particles, as this object applies a force to these fluid particles to change their momentum, to force these fluid particles around the object, Newton's third law says that these fluid particles will apply an equal and opposite force upon the object. Right? So, what happens is, now I'll quit that. Can I get, right, here we go. So, ink, right, and let's start out in black ink. So let's say that I've got, I don't know, some kind of object here, okay, and let's say we've got fluid flowing over that object, right? Okay, so something like this. We've got this object here with fluid flowing over it. Okay, my awesome drawing skills on display for the entire internet. Alright, so what's going to happen? Well, as this fluid flows over this object's applying a force to these fluid particles, meaning the fluid particles are applying an equal and opposite force back on this object. So those fluid particles are applying some force F to this object as the fluid flows over it. Okay? Now, if we look at the components of that force, we can break any force into its components. Now, I've drawn the fluid flowing across in what we might call the x direction, left to right. Now, the force, the component, there's going to be a component of this force that's going to be parallel to the direction of flow. And there's going to be another component of this force that is perpendicular to the direction of flow. So we're going to resolve that force there. Okay? The force that is parallel to the flow is what we call the drag force, F sub D. The component that is perpendicular to the flow is what we call the lift force, F sub L. Right? So again, total force being applied can be resolved into its two components. We call the components of this force the lift and the drag. Okay. Turn ink off. I don't think I've defined that here, so let's see. Can I get a... oh, let's just put the ink back on. Right? Yeah. I could... As you can see, my writing's... I don't know if I'd call my writing legible there. Let's do this. Let's say F sub D, the drag force. is the force, the external force, external fluid flow force that is parallel to the direction of flow. F sub L, the lift force. I've already said this in words, but it's important, so I'm going to write it down in the hopes that maybe you're writing it down too as you're taking notes. You are taking notes, right? You're not just watching these videos and then you're going to forget everything later. Trick your brain into thinking this is important. Listen to my words, process those into your own words, and then write them down. And then you're going to trick your brain into thinking this is important enough to remember. As I'm talking, I can't write and talk at the same time. The lift force is the force perpendicular to the flow direction. Right? So drag force is the force parallel to the flow. Lift force is the force perpendicular to the flow. Okay? All right. So what causes these forces? Well, it's a Newton's third law, because the object's causing the momentum of the fluid to change, requiring the object to apply force to the particles. Therefore, the fluid particles are applying equal and opposite force upon the object. How do we describe these? Well, drag force, the model tells us, it's 1/2 coefficient of drag times the density of the fluid. This is the density of the fluid flowing, times V squared, times the area, the front-facing or the cross-sectional projected area, the area facing into the fluid. We can, equation-wise, just solve for the drag force, and that's what you get, although that's not normally how we would find that. Normally we'd go through an analysis like we talked about in Chapter 7, when we talked about Buckingham-Pi theorem and dimensionless quantities, right? And remember, we said Buckingham-Pi theorem told us that this coefficient of drag is going to be a function of the Reynolds number. Right? We actually did an example of this in class. Right? We said this drag force, the dimensionless quantity associated with this drag force became what we call the coefficient of drag, and the coefficient of drag is we found to be a function of, based on the other phenomena involved, rho v, a characteristic length, and the viscosity, or the Reynolds number. So we need to know the Reynolds number to be able to describe the or to try to figure out the coefficient of drag. Now, you'll probably find some equations for trying to model some of these, and sometimes you can actually find those equations published, but they're normally not very simple. Most of the time we just have charts and graphs that we read these off of. Okay. Lift, we compute the lift the same way. Again, we're not going to focus too much on lift in this course. Other courses in aerodynamics some of you may go on to take, where you can focus more on those later. But that's not going to be our focus here. Okay. So how does one find, so we'll talk about the example here in a second, how does one find these coefficients of drag? We know it's a function of the Reynolds number, but that doesn't tell us the equation. It's not something we can just plug numbers into and solve for, right? So how do we know what is appropriate drag coefficient for our situation? Well, there's a textbook for that, kind of like we had with the minor loss coefficients we saw in the minor loss terms. Your text should have large tables where they'll give you drag coefficients, right? So based on parameters of these shapes and geometries, they'll give you drag coefficients, all these different kinds of shapes. You'll see then also sometimes throughout the text, I don't know if you can see this, and there's my alarm, it's a good place to stop. You can see they're going to tell you drag coefficients based on Reynolds numbers of different objects. All right, we'll pick back up there in a second. Loud pop.